All right, so in this batch of problems, what we're going to do is we're going to be working with geometry problems. So reading number 3, a furniture builder is designing a rectangular dining table with a perimeter of 140 inches. What dimensions will yield the maximum area, and what is the maximum area of this dining table? All right, so as we usually do with a word problem, we label our unknowns. So how about I draw a picture? So we have a dining table that I know to be rectangular in nature. All right, its dimension is going to have some length and some width. All right, and at this stage of the game, what we want to do is maximize the area, right? So we know area to be length times width, but the constraint is the perimeter, right? We're told that I only have 140 inches, or excuse me, 140 inches to basically design, right, the length and width of that. So if we go to our perimeter formula, right, we know perimeter is twice the length plus twice the width, and I know my perimeter is 140. So there's basically our constraint, right? This is our constraint, and here's what we want to try to maximize. All right, so we have everything we need to know. I've taken care of everything in the problem. However, what's missing, right, is we don't have a quadratic anywhere, right? This is length times width. They're both the first power. And this is length times width. They're both of the first power. So where's the quadratic? So what we do in this situation is we use the constraint to come and rewrite the area. So right now my area depends on two variables. I'm going to try really hard to make it depend on, let's say, the length in this case. So I'm going to come back over to my constraint equation, and I'm basically going to solve for W. So I'll subtract 2L from both sides, right? And that'll give us 2W equals 140 minus 2L. Divide everything by 2, and this gives us that W is basically 70 minus L, right? There's two fractions there. All right, so now that I know what W is, I'll come up to my area formula and substitute it there. So I have L, and we just found that W is 70 minus L. And so doing some quick math, this basically means that my area in terms of the length is 70L minus L squared. And if we rewrite that, this is negative L squared plus 70L. And lo and behold, after that work, we finally have what we want, right? We have a quadratic. The lead coefficient is -1, which means we have a parabola opening down. So to maximize this area, we basically have to find the vertex. So what is the length that maximizes this vertex? Well, how about we use the good old-fashioned vertex formula? So we have negative b over 2a. So in this case, my b is 70, so we have negative 70 over 2 times -1. So we get negative 70 over -2. A negative divided by a negative is a positive, so we end up with 35. So my length, right, in order to maximize this die, my length has to be 35 inches. What about the width? Well, I'll come back here. We know the width is 70 minus whatever my length is. So it looks like the width is basically going to be also 35 inches. All right, and then last but not least, what is the maximum area? Well, we can do this a couple of ways. We can plug in what we know for my length in this guy, or we can just come up here and use my formula, and I think that might be the easiest. So what's my area? It's 35 times 35, right? Length times width. So doing some math here, right? 5 times 5 is 25, carry the 2, that gives us 17. 3 times 5 is 15, carry the 1. So it looks like we have 5, 2, 1, 2, 1. So it looks like the area is 1,225 inches squared. So basically what I'm going to go back and tell the furniture builder, given this constraint And given the fact that you want to maximize the area of a rectangular dining table, that's actually a constraint in itself as well. I'm going to tell the designer, I'm going to tell the builder, you need to build basically a square table, a table that's 35 inches by 35 inches, and that's going to maximize the area of the table at 1,225 inches squared. All right, so that, as you can see, is a much harder problem than what we did before. It's always nicer to have a formula, but you kind of get a feel for the situation that needs to be maximized, the constraint that we have for the situation, and what we commonly do is we solve the constraint for one of my variables, and then we take that value, substitute it into my equation I'm trying to maximize, and that usually gives us a function in one variable, in this case in terms of L. And now we can start analyzing it with the math that we know, which is, in this case, we have a quadratic that's opening downwards, and we basically just do our quadratic information to solve it. All right, so there's your introduction to our first area problem. There's another one coming soon, but we're already a little over 6 minutes into this, so I am going to pause and come back in another video. Talk to you guys soon.